Hello everyone, I'm Dr. Shen, a Marie Curie Research Fellow from University of Southampton. Today I'm going to talk about structured light toward multiple degrees of freedom and high dimensions. First, let's have a look. There are how many degrees of freedom in light? Actually, we can summarize 6 basic degrees of freedom: space, time, amplitude, wavelength, phase, and polarization. But the degrees of freedom of light are not limited by these elements. For example, the orbital angular momentum, the OAM, revealing the helical phase of beam, is a combination of space and phase. Therefore, we can extend many degrees of freedom by combining the 6 basic degrees of freedom. Following this strategy, we can do many research. For example, if we consider the phase and the wavelengths together and to generate a wavelength and OMM tunable vortex beam, that would be very helpful for the application of wavelengths and OM multiplexing communication. As another example, we can combine the phase and the space together to explore spatial distribution of multiple vortices like vortex lattices and multi-singularity arrays. We also can combine more than 2 degrees of freedom. For example, we can combine time, amplitude, wavelength, phase together. We can do some research on structured paths, and that also inspires us to explore many nonlinear effects of optical angular momentum. It's a really hot topic recently. Okay, if we combine space, polarization, and phase together, that allows us to generate a spatial varied polarization in a structured beam. The vector vortex beam. The story starts from the vector vortex beam. Vector vortex beam is a space polarization non-separable solution of Maxwell equation. For example, the superposed beam with the 2 superposed modes with opposite optical angular momentum and orthogonal polarization. You cannot tell what's the orbital angular momentum only if you measure one of the polarization. If you measure the polarization as the right-hand circular polarized, you will know the orbital angular momentum is positive. On the other hand, if you measure the polarization as left-hand, you will know the orbital angular momentum is negative. Such a non-separability with orbital angular momentum and polarization is very similar to the non-separability in quantum entanglement. For example, the polarization entangled photon pair, where you cannot tell what the polarization state the particle is, only if you measure the polarization of one particle as horizontal polarization, you will immediately know the polarization of another particle is vertical, vice versa. The only difference is here in the quantum entanglement are non-local for the 2 entangled particles. Such quantum-like property has inspired many applications of vector beam with quantum classical connection. Well, in recent years, people have realized the quantum entanglement with multiple photons. The measure of one of these particles will affect another particle in this entangled system. This quantum classical similarity inspires us to think a question. Can we create a classical vector beam more than 2 degrees of freedom with non-separability that will transfer more quantum-inspired mechanics into our classical community? To this end, let's have a review how to extend degrees of freedom in conventional vector vortex beam. Okay, the 2 degrees of freedom are polarization and orbital angular momentum. Each of the states can be mapped on the Poincare sphere, treated as a quantum bit. And the vector vortex beam is just the tensor product of the polarization and OAM that results into a high-order Poincare sphere, representing the spatial variety polarized state. However, we can find a limitation here. In previous orbital angular momentum state, we only consider azimuthal mode, right? The L mode. There's only one mode in structured beam. The whole structured beam, including 3 modes, the 2 transverse mode and the 1 longitudinal mode. So the L mode is not enough for complete description. The more generalized the case should consider the two transverse modes and the one longitudinal mode together, and we can apply a SU2 transformation onto the state to generate the more general high-order OAM mode. The two transverse indices describing the singular structure at the two transverse directions, and another longitudinal mode describing how the beam is divergent upon propagation. The whole evolution of such a generalized state forming a family of Hermite-Lagrange mode, HLG mode. Well, we can do a more interesting further generalization. We use such a generalized OM panchaosphere as an eigenstate to form a more complex coherent state. That is a well-defined superposition of various frequency-degenerate eigenstates. We can always find a family of HLG mode that all the components has the same frequency, the same degenerate frequency described by a frequency ratio, so that we can use this mode as eigenstate to superpose a coherent state mode, and we use the form as SU2 coherent state because it has a very interesting properties, namely quantum classical correspondence. That means the wave packet distribution of such a state is always coupled with a classical moving trajectory. Similarly, if we use the coherent state to form geometric mode, such a mode will have an interesting ray-wave duality. The structure-like wave packet is always coupled with a ray trajectory described by the classical geometric optics. Such an evolution can be described by 3 degrees of freedom. The first one is the frequency degenerate ratio, omega, that determines the numbers of rays in the ray trajectory. Here is an example of omega equal to 1/6. That means there should be 6 rays in the ray trajectories. Second, the orbital angular momentum. Here the orbital angular momentum reveals the twisted degrees of the ray trajectory. The third one is the phi. Here it reveals how the ray sequence distributed in the ray trajectories. Then I will introduce how to generate such a ray wave structure light from a laser. As the frequency degenerate ratio is an important factor to determine the numbers of the rays in such a mode, so that we can control the longitudinal mode and the transverse mode frequency ratios in a laser cavity, such a planar concave cavity, by tuning the cavity length corresponding to the ray trajectory oscillating back and forth in the cavity. Actually, we can control 2 kinds of eigenphase state, the coherent phase state, 0 or pi, in the cavity, by selective controlling the bonding spot and the laser crystal in the cavity. For example, the 4-ray state, the phi equal to pi and the phi equal to 0 state are the W shape and the M shape respectively. Well, in previous work, we can only generate the pure ray wave trajectory by a defined frequency ratio omega and the coherent phase phi. Can we generate a superposed hybrid state by superposing 2 different kinds of ray wave coherent state together? We theoretically prove the existence of the hybrid state. If we can superpose 2 kinds of eigenphase state together and the 2 component trajectory can share a reflecting point on the same location, then we can locate our bonding spot onto this location to supporting such a hybrid state. We successfully generated such a ray wave non-separable state from a laser. In contrast to previous works, we use an anisotropic C-cut ND-validate crystal into the laser. Such a crystal has a very interesting property. If the input beam onto the crystal with an inclined angle, and there will be a polarization modulation onto the beam dependent on the inclined angle due to the birefringence of the C-cut crystal. This plays a very important effect on our ray wave non-separable states. The 2 component trajectory had different transverse size, That means the two ray wave trajectories would have different polarizations. Here are the experimental and simulated results of the hybrid ray wave non-separable state generation, and they agree well with each other. In order to introduce orbital angular momentum, we use the two cylindrical lenses as a stigmatic mode converter so that we can convert the planar trajectory into the circular twisted trajectory. And we can see that the hybrid non-separable trajectory state and the pure coherent state can be controlled by the off-axis pumping control. The pure trajectory state shows the polygonal pattern, and the hybrid trajectory shows the star-shaped pattern. Very beautiful. Here the left side shows the spatial wave packet distribution. The right side shows several results of the polarization measurement of the vector beam. At the 5-ray state, we can observe that the inner trajectory and outer trajectory with the smaller and the larger orbital angular momentum, non-separable with circular polarization and linear polarization. At the 6-ray state, we can observe more interesting results. Here shows the result that the outer trajectory shows a vertical polarization and the inner trajectory shows horizontal linear polarization. That means the 3 degrees of freedom perform as the orthogonal state. All of the 3 degrees of freedom are orthogonal state. That perfectly simulates the 3-particle quantum entanglement with a maximal entangled state. We also show the result of a scalar beam. The inner trajectory and the outer trajectory are both vertical linear polarization. The significance of the ray wave vector vortex beam is not only in its interesting spatial structure, it also has topological phase. For the cases of the vector beams, we can analyze the vector singularities, and we can observe the field are all full with singularities array. And when the beam performs as a maximal non-separable state, the multiple singularity array has the most complex structure, behavior like a flower shape. Very beautiful. The study of the topological phase of the ray wave structure beams allows us to design a computer-generated hologram to convert the very conventional Gaussian beam into such a very interesting ray wave duality beam. A very important advance of this scheme is that it can freely control more kinds of ray wave structure, breaking the limit of the laser cavity. For example, the ray wave pattern coupled with the Lissajous curves and the trichoidals that opens more degrees of freedom controllable in light. Okay, let's make a brief summary. The hybrid ray wave vector vortex beam opens many new degrees of freedom. Besides the conventional OAM and the polarization, we can also control the degenerate ratio and the ray trajectory phase. Can we find more degrees of freedom to be controlled in such a scheme? If we consider the ray state with more rays, there will be another new degrees of freedom to be controlled, that is trajectory combination. For the cases with more rays in the trajectory, it's possible to have more cases of such a non-separable superposition. For example, the 7-ray state, we can observe 2 kinds of superposition. For the 9-ray state and the 10-ray state, we can find 4 kinds of non-separable superposition. If we consider a stigmatic effect, we can generate a more interesting state that the ray distribution can be gradually changed from a linear array into circular star shape, and the astigmatic degree just as the new degree of freedom to describing such a topology changing upon propagation. In the above result, we only consider the degenerate state with a rational ratio 1/5, 1/6. However, a more interesting phenomena can be observed in the quasi-degenerate state, and the spots for each ray state can be connected to each other and formed a polygonal shape. And such a quasi-degenerate degree is a new degree of freedom to control such a multi-spot shape or polygonal shape in the ray wave structure beam. Therefore, The ray-wave duality structural beam opens a new door to explore more degrees of freedom to be controlled in structured light. Okay, let's go on to ask, what's more? There is still an important degree of freedom not used, the time. No matter how you improve your spatial structure, the resulting light is belong to the space-time separable solution of Maxwell's equations. There is another very important and a very interesting class of the space-time non-separable pulse. A typical example in which is the flying donut pulse. The flying donut has a very unique characteristic to be explored. A conventional transverse pulse can be regarded as the free space dipole excitation, the electric dipole excitation, but the flying donut is related to the toroidal dipoles. Its electromagnetic configuration can be regarded as the superposition of an electric dipole and a toroidal dipole, resulting into an anapole structure. That is totally a new chapter in electrodynamics and optics. The flying donut is a focused single-cycle toroidal pulse that the structure can be evolved from one cycle into 1.5 cycle upon the propagation, revealing the space-time non-separable structure. Another description is using the spatial spectral description. Equivalently, the space-time non-separable structure results into a very unique spectrum. That's the isodiffraction spectrum. The isodiffraction means the various wavelength components diffract at the same rate. The isodiffraction is more clearly demonstrated here. The left figure is the spectral distribution at a transverse plane, and the right one is the trajectories of various colors, the maximum position of various colors. As is seen that the various colors diffract at the same rate, and the blue light is always confined inside and the red light is outside. So that we can define two classical states to describe the interesting isodiffracting effect. The first one is the spectral state, lambda I state. That means the monochromatic component state of light of defined wavelength lambda I and with defined radial position of the peak intensity. And the spatial state is the total field state of light, located at the position with defined radial ratio of eta. The eta is the radial ratio, the radius over the constant radius, the R max. R max is the radius of the maximum total intensity. For an isodiffracting pulse, the spatial state and the spectral state are perfectly coincident. Each spectral state is located at corresponding radial ratios, and that the spatial state and the spectral state are non-separable, fulfills an entangled state. As a comparison, we also built a wideband logarithm mode, the LG mode. That is superposed by many colored LG mode components. These two pulse has the same donut shape and the wideband spectrum, but the LG pulse does not hold a good space-time non-separability. As it seems, after focusing, the various color components can have different focus degrees. So the spatial and the spectral states are surely randomly separable upon propagation. So there are possible many crosstalk terms in the general space spectral state. How to measure the spectral and the spatial entangled state in experiments? The first step is to detecting the spectral state. We can obtain the various spectral components by the filters for various wavelengths, and then find the maximum region correspondingly, and construct the classical field as shown in the gray band regions. For the spatial state, we should directly measure the whole field of the beam and record the various ring regions for each radius, and the radius is predicted by the ideal isodiffraction series. Then we can get the functions of corresponding spatial state. The next step is the state tomography. Akin to the quantum state tomography, we calculated the inner product of each combination of spectral state and spatial state. The tomography matrix allows us to find each coefficient of the tensor product state. The coefficients are Cij for ideal entangled state. The Cij is non-zero only if the I equal to j. So that means the space-time entangled state is corresponding to a diagonal tomography matrix. Since we know that the space spectrum state can construct the density matrix and calculate the many quantum measure concepts to characterize our space-time pulse. First, we calculate the fidelity. The fidelity in quantum mechanics is a measure of similarity of a measure state to the ideal state from 0 to 1. And in our simulation, we set the ideal state as the ideal flying donut pulse, and so we can measure the similarity of our measured pulse to ideal pulse. We also calculate the concurrence and the entanglement of formation, the EOF, to quantitatively measure the degrees of non-separability from 0 to 1. The 0 means the state is purely separable, and the 1 means the state is maximally non-separable. Here are the results for an ideal flying donut and a flying donut with noise, and the wideband LG beam and the monochromatic LG beam. The perfect flying donut is set as the ideal case. So the fidelity is 1. And after adding some noise onto the flying donut, the fidelity is decreased into 0.6. That means there is still some isodiffracting effect, but with some deviations. The wideband LG beam, we know that the is such about do not have the isodiffraction, so the fidelity is nearly 0, and the monochromatic LG beam is also fidelity is nearly 0, and the concurrence and the EOF of the flying donut is nearly 1. That means the ideal non-separability is perfect. That is decreased for the noised flying donut, and further decreased for the LG beams. And as an extreme case of monochromatic beam, the concurrence and EOF is exactly the 0. Such a spacetime non-separable pulse can be generated by a singular metamaterial array as a singular metal surface. We just need a conventional planar wave and convert it into a radial polarized light by radial polarizer, and then converted the radially polarized pulse into the flying donut by our designed singular metal surface. We measured our experimentally generated flying donut pulse with a fidelity of 0.8, so that we can argue our experimental flying donut pulse has a very good quality. In conclusion, non-separable state of light is very similar to the quantum entanglement, and we can transfer quantum mechanics to interpret the classical structure light. The hybrid real-wave structure can break the limit of conventional vector vortex beam to control more than 2 degrees of freedom, and such exotic structure can be directly generated from a simple laser and controlled by digital hologram. The flying donut is a spacetime polarization non-separable solution as a novel free space nanopode excitation. Such pulse can be generated by our designed metasurface, and the state tomography method can be used to measure the strength of spacetime non-separability of light. Here is the list of the important references of this talk, especially The LSA Optical Vortices Review paper is the ESI highly cited paper and hot paper, and the Optical paper on railway vector vortex beam is selected on the cover. Finally, I'd like to acknowledge the contributions of my current supervisor Nikolai Zerodov's group in ORC, Andrew Forbes' group in WITS South Africa, Liu Qiangfuxing's group in Tsinghua, and Yuan Xiaocong's group in Shenzhen University, and all the international cooperators and the supporting of fundings. Thanks for your attention. Please feel free to contact me if you have any questions.